Hello, everyone. Good to see you're here and ready to learn. You're almost done with the course. Now that we've added a storage and database layer, the employee directory application is fully functional, but we still have two more issues. The first issue is that we have no insight into how our application is performing and how it utilizes resources. So to fix this, we will start off the next lesson with a discussion of a monitoring tool called Amazon CloudWatch. After we understand what the demand for your application looks like, we'll address the second problem, scalability. You may find that your application demand isn't always constant, so in the last section of the course, you'll learn how to automate the process of adding resources as demand increases and reducing capacity as demand declines to reduce cost. You'll also learn how to deliver traffic and load balance across a changing amount of resources. Let's get started. When you have a solution built out of many different pieces, like how we build solutions on AWS, it's important to be able to see how different services are operating over time and react to operational events as they are happening. Let's consider the employee directory application. It's Monday morning and the users are seeing latency on page loads. It's probably not good enough to wait until a user sees the slowdown, calls, or enters a ticket saying, "Hello, your application is running slow." If you receive a call or a ticket from your users, you can then react and troubleshoot the issue. Waiting for users to notice and report issues to investigate will generally lead to unhappy end users. Ideally, you'd be able to respond to operational issues before your end users notice. On top of that, the end user can only provide information about their experience, and they cannot give insight into the inner workings of your solution. So they can report the issue to you, but where is that issue coming from? Is it an EC2 problem? Is it a database problem? Is it a code change that has recently been deployed? Without monitoring, you have to do some digging to figure all of that out. So what do we need to do? The first step is to put proper monitoring in place. Monitoring is a verb. It's something we do. We collect metrics, we collect logs, we watch network traffic. The data needed to help you pinpoint problems comes from the different services and infrastructure hosting the application, and monitoring tools help you collect the data being generated by these systems. In a cloud environment that is ever-changing and ever-scaling, it's even more important to collect various types of information about the systems as they scale up and down and change over time. The different services that make up your solution generate data points that we call metrics. Metrics that are monitored over time are called statistics. A metric is a data point like the current CPU utilization of an EC2 instance, where other data you monitor could come from different forms like log files. For example, your network will generate data like flow logs so you can see how network traffic is coming into and out of your VPC. The servers will be generating metrics such as how much CPU is currently being used or how much network traffic the instance is accepting at any given moment. Then finally, one more example is your database layer, which will generate metrics such as the number of simultaneous connections to your database. So you need a way to collect all of this information. Once it's collected, it can be used to establish a baseline, and this baseline can be used to determine if things are operating smoothly or not. If the information collected deviates too far from the baseline, you would then trigger automatic alerts to go out to someone or something to try to remediate the issue. A good monitoring solution gathers data in one centralized location, so you can proactively monitor and operate your system to keep your end users happy, as well as allows for automated tasks to be triggered based on the data coming in. This is where Amazon CloudWatch comes in. CloudWatch allows you to monitor your solutions all in one place. Data will be collected from your cloud-based infrastructure, so you can see things like database metrics coming from RDS or DynamoDB, alongside EC2 metrics, as well as metrics coming from other services making up your AWS solution. Coming up next, we'll dive into some CloudWatch features and use cases. In this video, I'm going to run through some of the features that Amazon CloudWatch has to offer. We've already deployed resources into our AWS account with the employee directory application. So to get a handle on what CloudWatch is and how it works, let's dive into the AWS console and see what we can see. The end goal of this demo is to set up a dashboard that shows us the CPU utilization of the EC2 instance over time and set an alert that will be sent out if the CPU utilization of the instance goes over 60% for a period of time. I'm already in the console and I will navigate to Amazon CloudWatch. A lot of the AWS services begin reporting metrics to CloudWatch automatically when you create resources. Let's explore what types of metrics are available from the resources that we have already created in a previous lesson. To do that, let's first create a dashboard. A dashboard in CloudWatch is a customizable page in the console that you can use to monitor your different types of resources in a single view. This includes resources that are spread across different AWS regions. I want to create a dashboard that shows me the CPU utilization over time for the EC2 instance hosting the employee directory application. So now I'm going to click Dashboards in the left-hand navigation, and then click Create a Dashboard, and we can then name this dashboard My Dashboard. AWS resources automatically send metrics to CloudWatch, and it's built into the service. I'm going to select which widget we can add to the dashboard, and I will select a line graph here. Next, we can take a look at what the data source will be for this widget, and I will select Metric for this. Now we can browse through all of the available metrics. This is organized by service, so I will find EC2. I will select EC2, and then I want to view per instance metrics. From here, I can scroll through the different EC2 specific metrics that are being reported to CloudWatch, and I want to select CPU utilization. Click Save, and now we are brought back to the dashboard with one line graph for one specific instance's CPU utilization. This gives us visibility into one aspect of the health of our EC2 instance. You can explore in your own account what other metrics are available for you through CloudWatch by default, but you can also report some custom metrics to CloudWatch programmatically. This is good to know because with EC2 and CloudWatch, you only get visibility into the health of the instance by default, which doesn't really give you a holistic picture of the health of your application. The application running on the instance might not be operating correctly, but the CPU utilization could be fine. So keep in mind that you may choose to use custom metrics to get a more detailed and accurate view of the health in these dashboards. Once a dashboard is created, you can then share it with your team members. Now let's move on to another feature of CloudWatch called Amazon CloudWatch Alarms. CloudWatch Alarms allow you to create thresholds for the metrics you are monitoring, and these thresholds can define normal boundaries for the values of the metrics. If a metric crosses a boundary for a period of time, the alarm would be triggered, and then you can take a couple of different automated actions after an alarm is triggered. In our use case, I want to notify someone if the CPU utilization spikes over 70% for a period of time, say 5 minutes. Let's create an alarm to do that. Let's navigate to the Alarm section and click Create Alarm. Now what I want to do is create an alarm for CPU utilization, so I will select Metric, click on EC2, Per Instance Metrics, and scroll down to select CPU utilization. Now I will select the time period we are monitoring to trigger the alarm, which in this case is 5 minutes. You want to make sure you pick a reasonable time period where you don't wait too long to respond, but you also don't respond to every short-lived uptick in CPU utilization. There is a balance to strike here, and it will be highly dependent on your specific situation and your desired outcome. Okay, so now I will scroll down and type in 70 for the static threshold which we are watching for, which is representing the CPU utilization threshold. If it goes over 70% for more than 5 minutes, it's likely that there's a problem. And now we will configure the action that will be taken if the metric triggers the alarm. For CloudWatch alarms, there are 3 states an alarm can be in: either in alarm, OK, or insufficient data. An alarm can trigger an action when it transitions between these 3 states. In our case, I want to have this send out an alert to an email address when it transitions from OK to in alarm. AWS has a service called Amazon Simple Notification Service, or SNS, which allows you to create a topic and then send out messages to subscribers of the topic. You can imagine a scenario where we have systems admins or developers on call for our employee directory application. And if something goes wrong, we want to send them an email paging them, letting them know that something is going wrong with the app. So we will select Create a new SNS topic since we do not have one in place already, name it CPU Utilization Topic, and then I will put in an email address here to receive the alert. Notice as I scroll down here that there are other actions you can take for a CloudWatch alarm. We will talk more about some of these options in upcoming lessons. So then click Next and give this a name and a description. And finally, click Create Alarm. It will take some time for the alarm to begin collecting enough information to leave the insufficient data state and transition into the OK state. That is it for now. We will continue to use CloudWatch in upcoming lessons to make our solution elastic through EC2 autoscaling.
At this point, you know how to set up alarms to notify you when your infrastructure is having capacity, performance, or availability issues. But we need to go one step further. We don't just want to know about these issues, we want to either prevent them or respond to them automatically. In this section of the course, you'll learn how to do just that. Currently, our infrastructure looks like this. We have one EC2 instance hosting our employee directory application in a single availability zone with DynamoDB as its database and S3 for storage of static assets. If I wanted to evaluate the availability of our infrastructure, I have to look at each individual component. I know that both DynamoDB and Amazon S3 are highly available by design, so that leaves one issue, this singular instance of our application. If that instance goes down, employees have no way to connect to our application. How do we solve this? Well, as you already know, to increase availability, we need redundancy. We can achieve this by adding one more server, but the location of that server is important. If instance A goes down, we don't want instance B to go down for the same reasons. So to avoid the unlikely event of, say, an AZ experiencing issues, we should ensure that instance B is put in another AZ. So now we have two instances that we've manually launched, but let's say our company grows rapidly and the employee directory application is constantly being accessed by thousands of employees around the world. To meet this demand, we could scale our instances vertically, meaning we could increase the size of the instances we have, or we could scale our instances horizontally, meaning we could add more instances to create a fleet of instances. If we scale vertically, eventually we'll reach the upper limit of scalability for that instance. But if we scale horizontally, we don't have those same limitations. I can add as many instances to my fleet as I'd like. But if I need, say, 15 more instances to meet demand, that means I'd have to manually launch those 15 instances and manually shut them down, right? Well, you could do it that way, or you could automate this process with Amazon EC2 autoscaling. This service will allow you to add and remove EC2 instances based off of conditions that you define. With this service, you can also maintain the health of your fleet of instances. But with more EC2 instances comes a bigger issue. How do we access those servers? Before, we were simply using the instance public DNS name or public IP address. But when you have multiple instances, you have multiple of IPs to route to. Instead of maintaining the logic to send requests to your various servers, you would use a load balancer to distribute those requests across a set of resources for you. And since you can connect from your load balancer to access the application, you no longer need to use the public IPs of your EC2 instances. Before the next video, I'll spin up two instances hosting our employee directory application. See you soon. Now that we have multiple EC2 instances hosting our application in private subnets, it's time to distribute our requests across our servers using the Elastic Load Balancing, or ELB service. Conceptually, how this would work is a typical request for the application would start from the browser of the client and is then sent to the load balancer. From there, the load balancer determines which EC2 instance to send the request to. After it sends the request, the return traffic would go back through the load balancer and back to the client browser, meaning your load balancer is directly in the path of traffic. Now, if we're looking at the architecture, the ELB looks like one thing. It looks like a single point of failure. But ELB is actually, by design, a highly available and automatically scalable service, much like S3 is. What that means is that A, the ELB is a regional service, so you don't have to worry about maintaining nodes in each availability zone or having to configure high availability yourself. AWS maintains that for you. And B, the ELB is designed to handle additional throughput and will automatically scale up to handle the traffic coming in, without you having to configure that feature. Now, there are several types of load balancers that you can choose. There's the application load balancer. That load balances HTTP and HTTPS traffic. There's the network load balancer that routes TCP, UDP, and TLS traffic. And there's the gateway load balancer that is mainly used to load balance requests to third-party applications. For our employee directory application, we'll be load balancing web traffic, so we'll be using the application load balancer, or the ALB. When you create an ALB, you'll need to configure three main components. The first component is a listener. The goal of the listener is to check for requests. To define a listener, a port must be provided as well as the protocol. For example, since we're routing web traffic and we set our application to use port 80, we'd want our load balancer to listen to port 80 using the HTTP protocol. Additionally, we could set up a listener port for 443 using the HTTPS protocol. The second component is a target group. A target is the type of backend you want to direct traffic to, such as an EC2 instance, AWS Lambda functions, or IP addresses. A target group is simply just a group of these backend resources. Each target group needs to have a health check, which is how the load balancer can check that the target is healthy so that it can start accepting traffic. The ALB operates on the application layer, which is layer 7 of the OSI model. This gives the load balancer a lot of cool features, and one of those is the third component, which is a rule. A rule defines how your requests are routed to your targets. Each listener has a default rule, and you can optionally define additional rules. So if we had two target groups, A and B, we can set up an additional rule that says if traffic is coming to our /info page, we can deliver that traffic to target group B. So because of the fact ALB operates on layer 7, you can customize paths for your traffic. Okay, now it's time to put this in practice. Let's create an application load balancer in the console. If you want to find the ELB service, you'll need to go to the EC2 console. So we'll type in EC2 to the service search bar, and then on the side panel, we'll select load balancers. Once we bring up our load balancers dashboard that shows all of the load balancers for this region, we'll then click Create Load Balancer. Here's where we choose which type of ELB we want, and you see the three main types. We'll be using the ALB. From here, we'll choose a name and call it app-ELB. The next setting asks if we want an internet-facing or an internal-facing load balancer. An internet-facing load balancer does what you might expect, which is route requests from clients over the internet to your backend servers or targets. An internal load balancer, on the other hand, will route requests from clients with a private IP to targets with a private IP. For example, if you had a 3-tier application with a web, app, and database tier, you could use an internal-facing load balancer to route traffic from your web tier to your app tier. For this app, we'll be routing internet traffic, so you can leave it as internet-facing. After that, we choose which availability zones we want to route traffic to. First, we'll choose the VPC, select both availability zones, and then choose the two public subnets. Now you choose your security group for your load balancer. This is where you decide which traffic you want to allow in. Here, we'll choose a security group that will allow traffic on port 80 from anywhere. Then, we configure the listeners and routing. Currently, the default setting is to allow HTTP traffic on port 80. If we want to allow or limit to HTTPS traffic, we can click Add Listener and choose HTTPS, but for this demo, we'll stick with the default. Next, we'll configure routing. And for this, we need to click on Create a Target Group. This will open a new page where we can configure the target group. First, we will select the target type, which will be instances. Then we can scroll down and we'll give it a name, such as app-target-group, and leave all of the defaults selected. Then we'll click Next to choose which instances we want to live in the target group. For here, I'll choose the two instances I've created in private subnets, and click Include as Pending below. And click Create Target Group. Now, coming back to the load balancer creation page, if we refresh the dropdown for target groups, we'll see the target group that was just created. We will select this and then scroll down, accepting the rest of the defaults and clicking on Create Load Balancer. After the load balancer has been created, we can then select it and find the DNS URL in the description box. We can then pull that DNS URL, copy and paste it into a new tab, and from here you can see our app. If I go to the /info page of our app, you can see which availability zone we're currently in. If I refresh the page a few times, you should see eventually that I'm being directed to both my EC2 instances in both AZs.
As more people visit our application, the demand on our 2 web servers is going to increase. At some point, our 2 instances aren't going to be able to handle that demand, and we're going to need to add more EC2 instances. Instead of launching these instances manually, we want to do it automatically with EC2 autoscaling. Autoscaling is what allows us to provision more capacity on demand, depending on different thresholds that we set, and we can set those in CloudWatch. Okay, so we're going to draw a high-level example of how this works, and then Ceph is going to build it for us. So, looking at our application, traffic coming in from the outside can come down to either EC2 instance. In this video, these EC2 instances will be part of an auto-scaling group. Each of the EC2 instances that we launch will be completely identical. Then we're going to run code to simulate stress on our employee directory application that will make the instances think that they're overloaded. When this happens, the instances will report to CloudWatch and say that their CPUs are overloaded. CloudWatch will then go into an alarm state and tell autoscaling, give me more EC2 instances. As each instance comes online, they will pass ALB health checks, they'll start to receive traffic and give us the horizontal scalability that we need. Ceph will be helping us build out the scalability. Let's have him join us. You got all that, right?
Yes, it's time to make this app scale. Let's make it happen. So to get this built out, the first thing we need to do is create a launch template. This is going to define what to launch. So it's all about setting the configurations for the instances we want to launch. Morgan said we want our instances to be identical, and that's what we'll be configuring here. First thing we're going to do in the EC2 dashboard is find launch templates on the side panel and click Create Launch Template. We'll first provide a name and description. I'll call this app-launch-template and give it a description of a web server for the employee directory app. Then you'll notice this handy checkbox that asks if we are going to use this launch template with EC2 autoscaling. We are, so we'll check it and scroll down. We'll then choose the AMI. Again, the launch template is all about what we launch. So what we want to do is create mirrors of the web servers hosting our app that we already have running. That way, whenever we scale out, we just have more instances with the exact same configuration. When we launched the instance hosting our app earlier, we used the Amazon Linux AMI and a T2 Micro instance type. So we'll select both of those options. Next, we choose the security group for our new instances. We'll use the same security group you created earlier in the course, the web security group. Then we scroll down and expand the advanced details selection. Here we'll choose our instance role, the same role we used previously in the instance profile dropdown. Once we do that, we'll scroll all the way down and paste our user data. This is what grabs our source code and unzips it so that our application runs on EC2. Now we're done and we can click Create. Now that we've configured our launch template, which again defines what we launch, we now have to define an autoscaling group which tells us where, when, and how many instances to launch. To create an autoscaling group, we'll select autoscaling groups on the side panel and then create an autoscaling group. Here, we'll enter a name such as app-asg, and then select the launch template we just created, app launch template, and then click Next. Then we'll select our network. We'll choose the same VPC we created earlier in the course, app-VPC, and select both the private subnets we created, private A and private B, and then click Next. We then need to select Attach to an existing load balancer to receive traffic from the load balancer we created earlier, and then choose our target group, App Target Group. Click Enable ELB Health Checks so that the load balancer will check if your instances are healthy, and then click Next. Now we'll choose the maximum, minimum, and desired capacity. The minimum we'll say is 2. This means that our auto-scaling group will always have at least 2 instances, 1 in each availability zone. The maximum we'll say is 4, which means that our fleet can scale up to 4 instances. And the desired capacity, which is the number of instances you want to be running, we'll say is 2. Next, we can configure the auto-scaling policies. With scaling policies, you define how to scale the capacity of your auto-scaling group in response to changing demand. For example, you could set up a scaling policy with CloudWatch that whenever your instance CPU utilization or any other metric that you'd like reaches a certain limit, you can deploy more EC2 instances to your auto-scaling group. So, what we want to do is use target scaling policies to adjust the capacity of this group. Earlier, Morgan created a CloudWatch alarm that resulted in the action of sending out an email. Here, we're going to create a target tracking policy, much like Morgan created the alarm, but this time it will result in the action of triggering an auto-scaling event. So we'll name this CPU utilization, and then we'll say that we want to add a new instance to our fleet whenever the target value is 60%. We'll also keep the instance's need setting at 300 seconds to warm up before scaling. Then we'll click Next to configure notifications when a scaling event happens. This is optional, so for now we're going to skip past it. All right, here we can review and click Create Auto-Scaling Group. Now all that's left is to stress our application and make sure that it actually scales up to meet the demand. To do that, I'll open up a new tab and paste the endpoint for our Elastic Load Balancer. Here's our application. I'm going to go to the info page by appending /info on the URL. You'll notice here that we built in a stress CPU feature. This is going to mimic the load coming into our servers. In the real world, you would probably use a load testing tool, but instead we built a stress CPU button as a quick and easy way to test this out. Then we can watch our servers scale with that auto-scaling policy. So as the CPU utilization goes up, our auto-scaling policy will be triggered and our server groups will grow in size. I'm going to select 10 minutes for our stress test. All right, some time has passed. We've stressed our application, and if we take a look at CloudWatch, we can see what happened. So let's click on CloudWatch. If you look here, we can see our alarm summary. We went over 60% CPU utilization across instances. That was our threshold, so we launched new instances. We launched 2 new instances into our auto-scaling group. Then you can see the loads start to come down. Because we've launched more instances into our auto-scaling group, there were more hosts to accept traffic for our Elastic Load Balancer, and the average CPU utilization went down across servers. All right, let's go look at the EC2 instances that were launched into the auto-scaling group. I'm going to go to the EC2 dashboard. From here, I'm going to scroll down to Target Groups and select the App Target Group. I'm going to select Targets, and we can now see that we have 4 healthy target instances in our auto-scaling group. So now we have an environment with an auto-scaling group and our launch template. We've set up an alarm in CloudWatch that whenever our CPU utilization goes over 60%, we're going to launch more instances into that group. All right, and this app should be able to scale now using EC2 auto-scaling.
Great, thank you, Steph. All right, now if we wait around long enough, what we would see is as the CPU load dropped off, then one by one they would each get terminated because we no longer need them, bringing our state all the way back down to the basic 2 we need, the minimum number for this particular group. All of that done without any human interaction. If for some reason you are doing this in your AWS account, don't forget to delete the auto-scaling group instead of the instances. Otherwise, guess what will happen? The auto-scaling group will spin up more instances to replace the ones that were deleted. So ensure you are deleting the auto-scaling group as well.
Hey y'all, and welcome to our final exercise walkthrough where we handled the load balancing and auto scaling for our application. As you can see, I am already logged into the AWS Management Console, and I'm using the admin user that I created earlier in order to handle these tasks. So in order to set up our load balancing and auto scaling, the first thing I'm going to do is launch the application instance. So I'm going to go over to EC2 and then go over to my instances and work with the last instance that I created. In this case, it's the employee directory app DynamoDB. So I will select that and I will go ahead and use the shortcut that we've been using where I click Actions, Image and Templates, and then Launch More like this. In this case, instead of appending DynamoDB, I am going to append LB for load balancing for this instance. And then I'm just going to scroll and make sure that everything is where I want it to be. So I want to make sure I continue using the same key pair. And then I also want to make sure that I enable the public IP so that I can access and test this instance. From there, I'm going to scroll down to the advanced details again, just to double check that my instance role is still selected and that my user data is where I left it. And from there, I'll go ahead and click Launch Instance. And now that that instance is launching, I can go over to View My Instances, and I will just give this some time to go ahead and be fully launched so that we can make sure that the instance is up and running and that the application is ready to go. All right, now that it has been a few minutes, I'll go ahead and click refresh again. And it looks like 2 of 2 checks have passed for this application instance. So just to verify that the application is up and running, I'll copy that IPv4 IP address and then paste that into a new tab. And it looks like our employee directory is up and running. And because it does have access to the S3 bucket and DynamoDB table that were created, the data that I had already added to the directory is still going to be visible, even though this is a new instance. So now that I've verified that that works, I can go ahead and close that. And what I want to do next is to create the application load balancer. So to do that, I do need to be in the EC2 console because the load balancers are accessed through the EC2 console. So the way that I get to the load balancing is I scroll down in this side navigation pane, and then there's this section near the bottom that says load balancing. What I want to do is click load balancers, and now that I'm in the load balancers page, I will go ahead and click create load balancer. And the type of load balancer that I want here is an application load balancer. So under that option, I will go ahead and click create. For my load balancer name, I want to go ahead and put in app-elb. And then I do want to make sure that this is an internet-facing load balancer so that I can access its endpoint from the internet. After that, I'll go ahead and scroll down. And under network mapping, I need to make sure that I select my app VPC, because that is where my instances are launched. That's where my instances for this application will be launched. And then for the availability zone mappings, I want to select both US West 2A and US West 2B. Once those are selected, you can see that it pops up with the ability for me to specify which subnets I want to route within. And I will go ahead and keep that with the public subnets for those availability zones. So scrolling down, I get to security groups, and what I want to do here is just make sure that proper access is set up for my load balancer. So to do that, instead of using this default security group, I'm going to go ahead and click create new security group, and that will take me to a page where I can do just that. I can create a new security group. So for this, I'm going to name it load balancer SG, and then my description is just, this is for HTTP access. The VPC for this needs to be my app VPC, so just making sure that that's the one that is selected. And then I want to work with my rules. So currently it has no inbound rules, so I'll go ahead and add a rule, and then add HTTP access from anywhere. And from there, I will go ahead and create my security group. So now that that security group has been created, I can close out that new tab and then refresh my security group list. And now I have the ability to select the security group that I just created. And that will be the security group that I use for this load balancer. Now that that's been done, I'm going to scroll down to listeners and routing. And this is going to be where I determine how my load balancer is receiving requests and how it's forwarding those requests on. So here I'm going to click create target group, and that will open up a new tab. I want to keep instances selected as the target type, and then I want to name my target group app target group. After that, I want to make sure that it's associated with the correct VPC, and then I want to scroll down to health checks. And health checks is going to be how the load balancer determines which instances are capable, or which targets are capable of receiving requests. Here, I want to expand advanced health check settings, and I want to make my healthy threshold 2 and my unhealthy threshold 5. I also want to make my timeout 30 seconds, and I want to change the interval of checks to 40 seconds. So what this does is, the healthy threshold is how many consecutive health checks that are successful are going to determine if the instance or if the target is available to receive requests. And unhealthy threshold is how many consecutive failed health checks determine which targets are not available to receive requests. For the timeout, this is just how long is it going to take for the health check to fail if no response is received. And then the interval is just how often are the health checks going to be sent. With all of those selected, I'm going to go ahead and scroll down and then hit next. And now I am able to register targets to my target group that I am creating. For this, I am going to go ahead and select the instance that I had just launched to include as a target, and then I'm going to select include as pending below. Now that that has been included, what's going to happen is I will create the target group, and then the load balancer will start those health checks to make sure that that instance as a target is up and running. So I'll go ahead and click Create Target Group. And that target group has been created. So since that target group has been created, I will go ahead and close this tab. And back on my load balancer creation page, I can go ahead and refresh my listeners and routing drop-down list, and I can select app target group, which I have just created in order to be utilized by the load balancer. Once I've selected that, I can scroll down and click Create Load Balancer. And now that the load balancer is being created, I can click View Load Balancer. And as you can now see, I have a load balancer that has freshly been created, and it is just currently being provisioned, and that will just take a couple of minutes. So after a couple of minutes, we can see that the state of the load balancer has changed to active. So what I want to do from here is just test to make sure that I can access my application from the load balancer. So to do that, I will select this specific load balancer, and what I want to do is copy the DNS name for this load balancer. With that copied, I will go ahead and open up a new tab, paste that load balancer endpoint in there, and as we can see, the load balancer is directing traffic to the application instance with the data that I have added. Okay, now that I can see that that works, I'm going to go back to the EC2 management console, and the next thing that I want to do is get everything ready for scaling. So the first thing that I need to do in order to do that is to create a launch template. So in the left-hand menu here, under instances, there's a selection for launch templates. I'm going to go ahead and select that. And because I don't currently have any launch templates created, I will go ahead and click Create Launch Template. My name for this will be App Launch Template, and my description will just be a web server for the employee directory application. From there, for auto-scaling guidance, I want to select this because I am specifically going to be focusing on EC2 auto-scaling. And then I want to scroll down and select the components that are necessary for me to launch my instances. What the launch template does is just it tells autoscaling what it is that I want to launch. So what instances, how to configure those instances, and all of the details that you would use if you were manually launching instances. So what I can do here is, since I do have instances already running, I can select currently in use, and that will bring up what I am currently running. And because my account only has one instance currently running, it will pull the information for that instance. For my instance type, I want to select a T2 micro because that is the instance type that I want to scale, and it's free tier eligible, so that will keep those costs down for this little exercise. For my key, I'll just keep selecting the same keys that I have been. And then for my network settings, I want to make sure that I select the security group that I created specifically for this. And so that is going to be my web security group. After I've done that, I'm going to go ahead and scroll down to my advanced details and expand that. And the two main things that I want to do here are I want to make sure that my instance profile is utilizing the role that I've set up for access to the other resources. And then I want to make sure that I add my user data in order to install and configure the application that I'm using. So to do that, I will go ahead and paste the user data in here. But then I just need to make sure that I change the necessary components so that I am working with the same resources. So I'll change my bucket to the bucket that I've created for this application, and I will change my region to US West 2 for the Oregon region. So once I've done that, I can create my launch template. And as we can see, my launch template has been successfully created. And if I go over to View Launch Templates, I can see the newly created launch template. From here, I need to create the actual auto-scaling group. So to do that, I am going to scroll down in this left-hand navigation pane, and under auto-scaling, I'm going to select auto-scaling groups. I don't currently have any auto-scaling groups, so I will click Create Auto-Scaling Group. The name for this group will be App ASG, and because I've created a launch template, I can go ahead and just select the launch template that was created specifically for this group. Once that has been selected, I can go ahead and click Next. And this is where I get to choose various launch options. So in this case, I want to make sure that I am launching into my app VPC, and then I want to launch these instances into my public subnets. So I will choose public subnet 1 and public subnet 2. With those selected, I can go ahead and click Next. And now I'm in my advanced options. The reason that this is important is because, for one, I've created a load balancer and I need to make sure that this auto-scaling group is utilizing that load balancer. So what I can do is attach to an existing load balancer, and then I can choose my load balancer from my load balancer target groups. From here, I can just drop this down and select App Target Group. And then for my health checks, I will just have the load balancer handle the health checks since those have already been set up. After that, I will click Next. And here is where I can decide how large and how small I want my group of instances or my fleet of instances to be. So what I'm going to do here is I'm going to change my desired capacity to 2. I also want my minimum capacity to be 2, and then I want my maximum capacity to be 4. This will mean that my auto-scaling group will launch with 2 instances, and then it will never get smaller than 2 instances. So if one of those 2 instances is deemed unhealthy, it will launch an instance to replace that. If there is a load on the load balancer and a load on the instances, then the maximum size that my fleet will be is 4 instances. And so that's what this group size is establishing. After that, I want to make sure that for my scaling policies, I choose a target scaling policy. And for this target scaling policy, I can change my target value for my average CPU utilization to be 60, and I'll keep the 300 seconds of warm up as the default, and that's just going to make sure that if I scale, the scaling is going to be based on my average CPU utilization across my fleet, and if that hits or goes above 60%, then it will launch new instances, but it will give those instances 300 seconds or 5 minutes to warm up and start passing their health checks before it does another scaling action. So now that that's done, I can go ahead and click Next. And for notifications, I am not currently going to add notifications for my walkthrough, but here you could add a notification and make that notification an SNS topic and utilize your email address so that you can be notified anytime a scaling action is taken. But instead, I'm just going to go ahead and click Next, and then Next again, and just quickly review that everything is where I want it before creating my auto scaling group. So now that my auto scaling group has been created, I need it to get everything to that desired capacity. And once it's there, I can test and make sure that my application is still accessible, and then I can test scaling. So before I test my application, what I want to do is go back to the EC2 console, and then under load balancing near the bottom of the left-hand menu, I want to hit target groups. The reason I'm doing this is that I want to make sure that before I start testing anything, that everything is running and is healthy. If I want to keep an eye on it, what I can do is click targets, and then as you can see, the auto scaling group has launched 2 additional instances, one in each availability zone, and they are currently healthy. So that means that my application is up and running, and I have multiple instances now that will be utilized whenever requests are made. And so if one were to become unhealthy or go down for any reason, I have the other instances there to still answer those requests. So to test my application and the scaling of the application, what I'm going to do is go back to the application page that I have open, and there's a stress test built into this application just to make it easier for this exercise. So what I'll do is append /info to the end of my URL, and that will take me to the page that allows me to handle some tooling. One of the things I can do is I can refresh this page, and it, as you'll see, it will go between the various instances that I have running and the availability zones that those instances are running in. So refreshing this will show that it's changing the instances and changing the availability zones that are being hit. But what I want to do to test this is utilize this stress CPU built-in test here, and I'm going to go ahead and stress the CPU for 10 minutes. So this is going to allow me to stress my CPU to get it above that 60% threshold and launch new instances. And so while I'm waiting for that to happen, I'm going to go back over to the target group and view my targets, and then I'm just going to periodically refresh this to see when new instances are being added and when they're healthy. So I'm just going to give that some minutes as I wait for those to launch. So now that I've given it some time, I'm going to just see if some new instances have been launched. So I'm going to go over to instances, and as I can see, 2 more instances have been launched in response to the scaling action that is happening because of the CPU stress that we initiated. So these instances will be launched, and then they will be added to the group of instances that are part of the entire fleet. I hope you enjoyed the course and that the exercises were helpful to you, and I'll see you in another course.
Nice work getting through this course. Let's take a look at how this architecture we built turned out. The employee directory application is currently being hosted across multiple EC2 instances inside of a VPC in a private subnet. These EC2 instances are part of an EC2 auto-scaling group, and traffic is being distributed across them using an application load balancer. The database is being hosted on Amazon DynamoDB, and the images are stored in S3. Beautiful. Looking at this from a maintenance perspective, you would need to ensure that your auto-scaling policies are working well with your expectations, and it would likely take some tweaking over time. You also would need to install security patches and updates for EC2, as well as keep an eye out for new instance sizes or types that might help you further optimize your solution. Now, this is really great, but as with everything built on AWS, there are multiple ways you can architect a solution and have success. It really depends on what you are optimizing for and what you are trying to do that will determine how you architect an application. That being said, what I want to do now is present to you an architecture that could be a wonderful serverless redesign of the employee directory application, taking full advantage of cloud-native services like AWS Lambda. I'm going to touch on some services we haven't covered yet in this course to give you ideas of alternative architectures. So, this employee directory application is a great example of a standard 3-tier application where you have the presentation layer, the application layer, and the data layer. The presentation layer is the user interface, the application layer is the business logic, and the data layer is the database. As things are right now, the Amazon EC2 instances are hosting both the presentation layer as well as the application layer. This is true because the EC2 instances have a web server running that is serving the content for the website, like the HTML, CSS, and JavaScript, which is the presentation layer. Then the same instances are also handling requests for the backend logic for viewing, adding, updating, and deleting employees, which is the application layer. What I want to do now is separate those two pieces entirely, having the front end of the website hosted separately from the backend application logic. It's important to separate the presentation layer from the application layer so that the instances are not overloaded by handling different types of requests at the same time. We're going to move the presentation layer to be hosted out of Amazon S3. S3 supports static website hosting, and therefore this is a great place for us to host the HTML, CSS, and JavaScript for our website. When you're hosting a static website with S3, you may think, well, my website isn't static, it's dynamic. It's pulling data from a database, so this isn't a static website, and therefore S3 would not work for this use case. This is where JavaScript comes in. JavaScript files have the ability to make HTTP requests and load dynamic content, modifying the static page to display results that come back from requests. So this should work well. The presentation layer is taken care of. Now I want to tackle the application layer. It used to be hosted on Amazon EC2, but let's go ahead and change this to AWS Lambda. This means that our employee directory application code would only be run in response to events being triggered by the front-end presentation layer. Now, you don't want your front end talking directly to your back-end code, so you would instead expose your back-end using an API. We would use the service Amazon API Gateway to host this API. Each action you could take on an employee would have its own method on the API. This API hosted on API Gateway would act as a front door to trigger the backend code, which we would host on AWS Lambda instead of EC2 as discussed. We could have one Lambda function handle all of the requests for employee data, or we could have one Lambda function for each action. We would keep DynamoDB for the database or the data layer, and we would also keep S3 for the employee photo storage. All of the access between these services would be handled via role-based access using IAM roles. One nice thing about this is notice how, because we built this solution in a modular way, we were able to swap out how we were handling the presentation and application layer while leaving the data layer totally intact with no modifications. That is the type of flexibility that can help you innovate and adapt quickly to changes. So now, for completeness and clarity, let's focus on the new architecture and fill it out a bit more. I will add some other AWS services to this diagram that you can explore on your own. First, I'm going to add Amazon Route 53 for domain name management and Amazon CloudFront here as well, which will allow us to cache those static assets like the HTML, CSS, and JavaScript closer to the end users by taking advantage of AWS Edge locations. If a user wants to visit the employee directory application website, and view all of its employees, here's the flow. The user would first type in the domain for the website, which would get sent to Amazon Route 53. Route 53 would send back to the client the address of the static website being hosted on S3, and then the website would be rendered in the browser. This website has JavaScript making the API calls to the backend to load the dynamic content. So the API call to load all of the employees would be made, and it would hit API Gateway first. API Gateway would validate the request and then trigger the backend Lambda function. The Lambda function would then send an API call to DynamoDB to query the employees in the table, and it would return that data to API Gateway, which would then be returned to the JavaScript, which would finally be rendered on the page. All right, and that's that. With this architecture we just laid out, we have optimized for scalability, operational overhead, and depending on your usage, it could also be optimized for cost. The serverless aspects of this make the operations for support much less than compared with Amazon EC2-based workloads. There is no patching or AMI management when you use serverless solutions like AWS Lambda. Also, notice how it was not required that I create a VPC, subnets, security groups, or network access control lists for this solution. The networking aspect of this is managed for you, though you can integrate serverless services with your VPC if you need to for compliance reasons, but it's not required to get a solution up and running. You have many options to choose from when designing your application. You can imagine a scenario where you redesign the same application to be hosted using AWS container services, and then this entire diagram would change again. There are a lot of ways you can build on AWS, and that's the beauty of it. You can swap certain pieces of your solutions out as AWS services are released or gain new features. And because everything in AWS is an API call, you can automate the process along the way. That's it for this course. From me, Seth, Meowsy, and Fluffy, thank you so much for learning with us. One more reminder to please remember to delete any resources that you've created in your own AWS account for this class to avoid incurring any costs if you've been following along. Thanks again, and see you next time.